Hello and welcome. My name is Andrea Stocci, and this will be a presentation on predicting climate change with machine learning with ClimateWins. As climate change escalates, global weather patterns becoming ever changing and really erratic. The rise in these extreme weather events poses huge risks on the safety of numerous communities and industries. So to safeguard human health and well-being, ClimateWins is leveraging machine learning to accomplish the following objectives: to detect weather patterns that deviate from the regional average in Europe, assess whether these unusual weather patterns are on the rise, project potential future weather conditions for the next 20 to 50 years based on the existing trends and historical data, and finally, to identify the safest locations for people to reside, such as refugees, in Europe over the next 25 to 50 years. To do all this, we've classified into three main hypotheses and three main experiments. First is to classify unusual weather. So using hierarchical clustering, we can go beyond classifying atypical versus typical weather to find actionable categorizations. The second will be to generate accurate predictions. Using a generative adversarial network, or GAN, to synthesize weather data, we can train a convolution neural network to predict possible future conditions over the next 50 years. And finally, experiment 3 is to identify safe living regions. We're doing this by optimizing the random forest model. We can identify the most important weather features to track and use that information to identify safe living regions. So, the required machine learning models. First, the hierarchical clustering. This classifies each data point, combining the leaves, the data points, into branches according to their similarities. This outcome, as you may see here on the right, resembles kind of an upside down tree, and each category is depicted by a different color. The benefits of this model is that it generates new classifications from existing data, and it doesn't require pre-categorization. The system does it all. The model does it all for you. Random forest. This model organizes data through various decision tree models that classify the data points using true or false binary methods. A random forest trains each tree on a random subset of the data and averages the outcomes to generate a final prediction. This is amazing because one of the phenomenal advantages of a random forest is that it reduces overfitting through the averaging process, and it also provides clarity through visualizations. Then there's the CNN. So by utilizing hidden layers, the CNN identifies the features of a data set and generates classifications. Hidden pooling layers condense the data into average and maximum values, so also decreasing the computational power needed. The benefits of this are it effectively analyzes images, including radar-generated graphics, and is capable of analyzing very complex data and minimizing the output power or the computational power needed. Next, we have a general adversarial network. So this system has a generator network, creates synthetic data derived from real data points. Meanwhile, a discriminator network evaluates both types of data and tries to distinguish between the authentic and the artificial. The generator then utilizes this feedback to produce more convincing fakes until it finally can fool the discriminator. So the benefits of this is that we can create weather data that looks and behaves like observed conditions. So this increases the amount of data available for modeling, which is huge. To increase the depth of this analysis, some additional data will be necessary. First, like weather event data. So documentation of extreme weather occurrences throughout Europe, things like storms, heat waves, severe cold, earthquakes, and so on and so forth. Radar imagery. So with the radar imagery, so we'll need it related to the areas covered by the weather stations utilized within the analysis. Healthcare data to see data on illnesses, injuries, fatalities, all linked to extreme weather conditions in Europe. And finally, hazardous weather classifications. Define the definitions of what qualifies as dangerous weather. So then that could be further developed using the aforementioned data sets. And here we get into the actual experiments. Experiment 1 was classifying weather using hierarchical clustering. So the hypothesis was using hierarchical clustering, we can go beyond classifying atypical versus typical weather to find actionable categorizations. So how do we approach this? Well, to evaluate the feasibility of this model, we generated a dendrogram utilizing data from existing weather stations. We applied principal component analysis to minimize the number of dimensions, ensuring optimal resource utilizations. The results that we gathered were there was two main dendrograms that proved to have the best results. The first was the complete dendrogram, the complete method, which is on the top left. As you can see, it has three main groups, one in green, one in orange, and one in red. These probably are good weather conditions to mildly severe weather conditions to severe weather conditions. And the Ward method, which is on the bottom left there, as you can see, has actually got two main categories, which probably stand for pleasant weather conditions and unpleasant. So the next step for this is to enhance the value of this analysis. We suggest incorporating additional modeling approaches. Our recommendations include executing this model across multiple years, seasons, and months of data to facilitate result comparisons, and then leveraging the findings to bolster other and more definitive modeling techniques. Our second experiment was synthesizing data to improve predictions. So we use the GAN here to synthesize weather data that we can use to train CNN model to predict possible conditions over the next 50 years. So in the approach here, first was to run a Bayesian optimization on the CNN model to evaluate its accuracy, and then use a GAN to synthesize realistic weather data to then run through the CNN model. So the Bayesian optimization improved the accuracy of the CNN model from an accuracy of 12% and a loss of 60,413,308 to an accuracy of 91% and a loss of 0.2606, whilst the GAN produced data with an accuracy of 75% and a loss of 0.119. So the next steps for this would be obtain the recommended radar data and perform Bayesian optimization. Run the optimized CNN model utilizing the GAN generated data to improve the quality of the data generated by the GAN for the CNN, and incorporate a larger and more diverse set of images for training. Then we can analyze the result across different years, countries, and regions. Experiment 3, to assess the regions using a random forest model. So the hypothesis here was by optimizing random forest model, we can identify the most important weather features to track and use that information to identify safe living regions. So what was our approach here? Well, here we refine hyperparameters for a random forest model using grid and random search methods, and then compare the unoptimized and optimized results of weather data analysis. So the results showed that there was an accuracy of 96% in the unoptimized model, went up to 100% in the optimized model in the 1990s. Running the optimized and unoptimized model allows us to weigh the feature importance in climate analysis that we can see on the left. What are the next steps? We'll conduct an optimization process on additional weather stations and across various decades, apply the optimized model to extreme weather data, and compare the results with healthcare data to establish correlations with human well-being. So the recommendations. Data indicates that ClimateWins will gain the greatest benefit from allocating resources towards the optimization of GAN and CNN for weather prediction. This experiment demonstrated the most significant and the most improvements in our accuracy. The project exhibited immediate potential for meeting essential objectives. Data and algorithms needed, so the CNN, GAN, and by Asian optimization algorithms, data on extreme weather events, radar imagery, and classifications of hazardous weather conditions. The next steps will be to enhance the Bayesian process for the CNN, execute the CNN using GAN-generated data, and collect and prepare supplementary data. Thank you very much. My name was Andrea Stocci. My email is below and also the GitHub repository. Thank you very much.